Um, yeah. Just a second. Let me check some other textbook and oh, yeah, something like this. So here. So here. So okay, here if I have a claim that A is on n by n matrix with the ij entry equals to b I plus the j. Okay, so suppose I have such a matrix. Then, for example, so, so let me erase this for now. So for n equals to 3, A will be the first row, first column entry will be 2, then 3, 4, 3, 4, 5, 4, 5, and 6. Okay, so when n equals to 3, first row, first column entry is 2. First row, second column entry is 3, and so on. So such a matrix. Okay, so for such matrix, my claim is that for any n, for any integer n, for any positive integer n, the determinant of A will be 0. That is my claim. Then is it true or false? For this 3 by 3 case, it is 0. I mean, it is 0. Determinant is 0. You can consider 4 by 4 or 5 by 5, okay? And those will have all 0 determinant. Then how can I prove that? How can I prove, okay? So what if my question is prove the claim if it is true and find the counterexample and find on counterexample if it is false. So if you believe it is true statement, then you need to prove that statement. And if you believe it is false, then you need to find one example, one counter example that this claim does not hold, right? And so if you just try 3 by 3, 4 by 4, that do not prove the statement, right? If we want to prove, then you need to consider general n value. But we have infinitely many n values, so you cannot just try a few examples. Okay? So please check this, right? But the answer, it is false. So the claim will be true if you consider n greater than or equal to 3, but false for n equals to 1 or 2. And when n equals, so if I consider n greater than or equal to 3, the matrix will be always have zero determinant, right? Because how can I claim this? In case of 3 by 3 matrix, 3 by 3 matrix does not generalize, but we can get some hint, right? Because for this 3 by 3 matrix, given this A, if I multiply -1 to the first row, okay, before I do that, given this, if I multiply -1 to the second row and then add it to the third row, so in other words, if you subtract the second row from the first row, the matrix becomes 2, 3, 4, 3, 4, 5, and 1, 1, 1. And these two matrices must have the same determinants, right? And then if I multiply -1 to the first row and then add it to the second row, in other words, if I subtract the first row from the second row, then the matrix becomes 2, 3, 4, 1, 1, 1, 1, 1, 1. These three matrices must have the same determinants because I just performed replacement operations 2 times. But in case of the third matrix, its determinant will be 0 because it has 2 identical rows, right? That was one of the statements we just observed. So the matrix will be, and I can generalize this idea. If I consider any general, any non-negative, any positive n, the statement will be false. But if I consider n greater than or equal to 3, the statement will be true, right? And oops. Another example will be a matrix with the ith row jth column entry is I times j. Okay? I times j. So for example, when n is 3, you get 1, 2, 3, 1, 2, 3, and 2 times 2 is 4, 2 times 3 is 6, 6, and 9. Okay, so that is the matrix I want to consider. And as you can, and when n is 2, you get 1, 2, 2, 4. And when n is 2, you get 1, 2, 2, 4. And these matrices have 0 determinant. So for that matrix, determinant of A will be 0 for all n greater than or equal to 2. When n is 1, it does not have 0 determinant, but For any 2 by 2 or larger, such matrix will have zero determinant. Now, this is true. So, but for this, to prove this, cofactor expansion may not help, right? So I need to consider some other general properties of the determinant. So the point is, so if I know the specific value of n, and if I know all the entries of the matrix, then any method is fine, and people usually apply the row operations to simplify the matrix, to convert the given matrix into a triangular matrix, and then find the determinant there, and then trace back all the calculations to find the determinant of the original matrix. But if the matrix is large, or if the matrix contains any unknown value, some parameter, or if we do not know the specific value of n, okay, in that case, then you need to apply some, yeah, I mean, oh, if the entries of, I'm sorry, so let me split this. So if the entries of the matrix are unknown, then probably you want to consider the cofactor expansion. Now, if your n is unknown, okay, if your n is unknown, if n is not fixed, okay, then if n is not fixed, use some general properties to get the determinant. Okay. So, oh, and what else do I have? Mm, okay, and yeah, yeah, probably. Oops. Um, yeah, probably that's it. Yeah, that's probably you need to know. And then let's go to the final section. So in section 5, we want to consider some, we want to compare the cofactor expansion with this new approach. So here we say, here delta is a function from n by n matrix to some scalars. So some field f. So this f may be f, it will be real, or the set of complex numbers. Given this map, the function delta, we say delta is n linear function if it is a linear function of each row when the remaining n minus 1 rows are held fixed. That is the property we already observed. Okay? So we say this mapping is n linear function if it has a linearity on one row. So if one row, say rth row, is u plus k times v, here where here k is a scalar and u and v are some row vectors, then when this when these three matrices have the same n minus 1 rows. Only rth row is split. Okay, so here u and v are row vectors, and k is a number. If your delta satisfies this property for each row, then we say this your delta is an n linear function. Okay. And additionally, we say this n linear function delta is alternating if whenever your matrix has two adjacent if whenever two adjacent rows of A are identical, if delta maps such matrix to 0. Okay, so for example, if I have say 1 2 3 1 2 3 4 5 6, then delta will map this to 0. Okay, so if my delta is an n linear function, and if that n linear function is satisfies that property, then we say it will be an alternating function. Okay, now theorem 4.10 is very interesting. If your delta is an n linear function and alternating, then when your matrix A is transformed to B by interchanging two rows, then delta will have the opposite sign. And if your matrix A has any two identical rows, then delta of A will be always 0. Now, in case of the definition, the alternating does not specify the case of the matrix like 1 2 3 4 5 6 1 2 3, because even though this matrix A has two identical rows, but these two rows are not adjacent. Okay, but I can prove that whenever this matrix has any two identical rows, then delta of A must be 0. Okay, because if you interchange these two, the resultant matrix must have 0 delta. If you interchange these two, you get 0 delta value as well. So if you use this effect properly, then you can show that whenever matrix has any two identical rows, then its delta must be 0. You can prove it. If I use this effect, actually most of them were already proved in our class, right? And delta, suppose that my delta is alternating and linear function. Okay, and if I consider the replacement operation, if B is obtained from A by adding a multiple of a certain row to another row, so that means we are considering the replacement, then delta value is not changed. Okay, so here moments ago, so as we observed, this definition considers the case of scaling. If your function is n linear function, right, delta of matrix with say A1 up to AR minus 1 and k times AR and AR plus 1 up to AN. And if I consider matrix with only A1 up to AN and AR without K, and this delta value, then that will be k times this. That is the definition. That is the property obtained from the definition of being n linear function. So this effect, this scaling, comes from this definition of an n linear function, and this interchange operation, the effect of interchange operation comes from this 4.10, and that requires being alternating. And if I combine this, I can show that the replacement does not change the delta value as long as your delta is an alternating n linear function. And if your matrix is not invertible, then delta will have 0 value. And so we already observed the effect of the elementary row operation. So delta will have delta of E1 will be E1, E1, the elementary matrix corresponding to the type 1 row operation. Then E1 is obtained from the identity matrix. So delta of E1 will be the negation of delta I, identity. And in case of E2, delta of E2 will be obtained by multiplying the scaling factor to the delta of the identity matrix. And in case of the type 3, the replacement, delta of E3 will be the same as delta of the identity matrix. Okay? So what remains would be the value of the delta of identity matrix, right? So if I know the delta of the identity matrix, then I can find delta of any matrix. Okay. And suppose that delta of the identity is 1. In that case, delta of the product of these two will be the product of the determinant of A times the delta of B. And if that's the case, if delta of identity is 1, actually this is determinant of A times determinant of B, and that equals the determinant of A times B. Because if your delta identity is 1, then delta of A must be the determinant of A. The point is this, okay? The reason I'm explaining this is this. The determinant of determinant, okay? So the cofactor expansion, that can be written, that can be viewed as a mapping delta, okay, which is alternating and linear function, and which maps identity to 1. Okay, so that was verbally explained explicitly in certain theorem at the end of, say, it was section 3, I think. Okay, so we considered this the delta previously, right? And then we assumed that this my delta is an n linear function, even though we didn't use that expressions, but we assumed that that delta is a function which is a linear for each row when the other rows are held fixed, and this delta will have the will change the will have zero determinant when two rows are identical and delta of identity matrix is 1. If you consider a delta mapping satisfying those three, then that will be the same as the determinant. That was one of the theorems we considered previously, right? Anyway, the point is, if I consider if I need to consider the determinant, there are two ways. Okay, that is the point. You may consider the determinant of A as given in the definition based on the cofactor expansion. You can use this. And as I said, if you know the value of n and if you know all the entries of the matrix, then this cofactor expansion may be used, maybe a simple way to estimate the determinant. Okay? But I can find the determinant of the matrix by considering this determinant as a mapping, which is n-linear, meaning it will be a linear function for each row when I fix the other rows. Okay? And secondly, it is alternating, meaning when when two rows of A are identical, it will be mapped to 0. Okay? Thirdly, determine the delta of the identity matrix will be always 1 regardless of the size of the matrix. So if I consider some mapping satisfying these three properties, then determinant is the only function satisfying those three properties. Okay, mathematically speaking, if I consider such mapping with those three conditions, being n-linear, being alternating, and sending the identity matrix to 1, then this this condition, a mapping with those three conditions, definitely exists. Okay, if I consider a certain mapping which does not exist, then it doesn't make any sense, right? So so if I consider certain mapping, there should be several functions satisfying those properties. And if I consider this delta from n by m matrix to certain number, real or complex, okay? If I consider some mapping which is n-linear, alternating, and maps identity to 1, then that is well defined, first of all. So that mapping is well defined, meaning such a function definitely exists. And more important statement is that it is unique. It is unique. And that unique function will be the determinant function. So determinant can be obtained by considering this cofactor expansion or based on this viewpoint of delta. Okay. That is the main part of this theorem 5, section 5. Okay. So, yeah. So, just a second, let me. So, okay. So, if I consider some auto statement, so suppose that I have a 3 by 3 matrix A, and suppose that A has 3 rows, say A1, A2, and A3. Okay. And so I didn't specify the entries of the matrix, but I just give some property. Say, okay, for this matrix A, determinant is 6. Okay. Then what will, so, and then if I define matrix B by A1 plus A3, A3 plus A2, and A2 plus A1, then what is the determinant of a B matrix? So there are several ways to get the solution. Okay. Now, how can I find this? I mean, if this is a multiple choice problem, then probably you can just guess this solution. But if I ask you to prove this, I mean, if I ask you to find this with certain supporting statements, then you need to be logical. Now, how can I find the determinant? So the determinant of B, first of all, is the same as determinant of using this n linearity, A1, A3 plus A2, and A2 plus A1, plus determinant of A3, A3 plus A2, and A2 plus A1. Okay? And then using this n linearity one more time on the second row, that is determinant of A1, A3, A2 plus A1, and A1, A2, A2 plus A1. And if I apply the n linearity on the second determinant, that would be A3, A3, A2 plus A1, and A3, A2, A2 plus A1. And then if I consider the n linearity one more time, A1, A3, A2, A1, A3, A1, A1, A2, A2, A1, A2, A1, A3, A3, A2, A3, A3, A1, and A3, A2, A2, and A3, A2, A1, right? Then when I look at these rows, the second matrix has 2 identical rows. The third one has 2 identical rows. And the fourth one has 2 identical rows. Fifth one as well. Sixth, seventh. So they have all at least 2 identical rows. So their determinants will be all zeros. So this is a 0, this is a 0, 0, 0, 0, 0. And for the first matrix, if I interchange these two, the sign will be changed. And here, if I interchange first and third row of the last matrix, you also change the sign. So since determinant of A is 6, this value will be negative 6 minus 6, which is negative 12, right? So in this way, I don't have to perform the cofactor expansion, okay? But I could find the determinant of the matrix, right? And that was one of the previous exam problems. And yeah, yes, so and if I define delta, okay, as in the textbook, say n by n f to f, and that is alternating n linear, then in the textbook we observe the several properties of such mapping, right? The, so the question is, if M has rank less than n, then how can you show that the delta of M is 0? I mean, when you prove this, you can use the properties of this delta mentioned here in section 5. So you don't have to prove these statements, okay? But I will assume that you are familiar with these theorems, okay? So we have theorem 4.10, which mentions that when M has rank less, when if this matrix A has two identical rows, then its delta value will be 0. Okay. And I will assume this, okay? And you may use, if you want, you may use this one as well. But I want to check this one. So in that case, how can I prove that? Using the other statements. So please think about it. So, so as I mentioned, we have two viewpoints for the determinant. I mean, the technical calculation, say, the finding the volume of parallelogram or parallelepiped in space using the determinant, that is a trivial. That is a problem which everyone can solve, right? And I'm not that interested in that kind of topic. Okay, we need to understand the basic concept and of the determinant, and there are two viewpoints. One is the approach based on the cofactor expansion. Okay, the other is the viewpoint based on a function delta. So determinant as a using this delta is quite important. So you need to be familiar with this viewpoint. Then as I showed here, even though I didn't specify the entries of the matrix A, we could find the determinant of that matrix. Or yeah, we already have several some examples. So please check those. Okay, and what else do we have? Of course, you should. How about this? A and B are n by n matrix, say 3 by 3 or 5 by 5, when I give you this large matrix, then please do not assume that A is filled with several numbers. Okay, so here A and B are some general 5 by 5 matrix. Then here's my claim. Any general matrix, determinant of AB minus BA will be 0. Is it true or is it false? You can consider any matrix to guess the answer. If you think of some specific matrices for A and B, then you can find the corresponding value. And that value may help you to answer this question. But so if you consider some specific matrix, so when I give such a problem, some students think of a specific example. And then they say, okay, it is true because my example satisfies that statement. So the answer is true. So if you claim like that, that is not mathematical proof. Okay? The proof means the statement must hold for any matrices A and B, right? So in that case, you should consider some general situation, assuming A is filled with some 25 numbers, B is another matrix with 25 numbers, and okay, something like that. So how can I prove this if it is true? If you think it is forced, then why do you think it is forced? So you need to answer that question with some reasonably or mathematically. Okay, something like that. That something like those may be given in the exam, and those are some examples of the past final exam. Okay, so okay, and since we are done with the class, so okay, so let us consider some problems. So in the past, here is the problem I gave. So this is a true force problem. If you believe it is true, you can mark it true. If you believe it is a force, then you can mark a force. Say something like that. If I have a mapping T from 2 by 2 with real entries to R4 space, okay, defined by T of A is trace of A, trace of A transpose, trace of E times of A, and trace of A times E, where E is 0, 1, 1, 0 matrix. Okay, and of course, trace of A, B, C, D will be A plus the D. Okay, so if I have such mapping, then my claim is that this T so my claim here is that T defined by this is invertible. So how can I prove this? Well, one hint. I didn't give I didn't give the solution the other day, but you can find the matrix corresponding to this T with respect to certain basis, alpha and beta. You need to choose alpha and beta yourself, okay? But yeah, so that was given the other day, and yeah, another true false problem we considered. I like true false problems. Sometimes I request a certain proof. Sometimes I just request just the answer only. So it depends. So for some simple ones, I request the proof or counterexample. But if the statement is difficult, I usually just request certain answer only. So here is another problem. If so here A and B satisfy. So if two matrices A and B satisfy, so I sub 5 is 5 by 5 identity matrix. Then A cannot have more columns than rows. Okay. So when I say two matrices, so A and B, they don't have to be 5 by 5. Please remember that. Oops. Let me change this. This should be B times of A. Okay. So in that situation, so A and B may be certain metrics of certain sides, okay? But their product will be a 5 by 5, okay? In that case, the claim is that A cannot have more columns than rows. So what do you think about that? Is it true or is it false? Okay? So something like this. So these were some past problems. Okay. Sometimes I give you a specific matrix like 3, -1, 2, -5. This is in the textbook, I guess. -1, 2, -1, 2, 1, 3, 2, 8, 3, 3. And then I may ask you to find the determinant and rank of the matrix. You can find them, right? So since this is a 4 by 4 matrix, and with some numbers, so there are two ways. You can consider the cofactor expansion along certain row or column, or you can transform this matrix A to an upper triangular matrix and find the determinant of that upper triangular matrix. And then you think of all the matrices in between and then consider their determinants based on what kind of row operation you performed. Or you can apply the cofactor expansion, right? So You can, but in that case, your determinant will be written in terms of four determinants of 3 by 3 matrices. And that additionally requires certain coeffective expansion as well. So it it depends on you, okay? Your choice. So you can consider that. But since I'm asking the rank of the matrix as well, probably in this case, you want to consider the row operation to transform this A into an upper triangular matrix. Then you can solve this determinant and rank, okay, by just one approach, right? So you can consider this, or okay. And what is this given? Okay, then, so suppose that here is another interesting problem. Say P2R to P2R defined by T of f of x is given by f of x plus, say, f double prime of x, something like that. And beta is a certain basis. Well, I will give the basis explicitly, like, okay, like standard basis. Then probably you can derive this matrix, right? Right? But derivation of that matrix is not in the coverage of the final exam, but it was considered already in the middle term. So instead of asking fine to write down this, I want to express this matrix as a product of elementary matrices. Okay? Now, the answer is not unique because depending on your row operations, the corresponding elementary matrices may be different, right? But so, but anyway, we can write down this as a product of elementary matrices. So these were some problems in the past, okay? So please just think about it, okay? And then let's, even though it is 4 minutes left, so let's call it a day here. And then next Tuesday, we will have a class, okay? This is not the end of the semester. We have a class next week, okay? So please come to the class, okay? Next week, okay? And as you know, we have the final exam on 16th, right? So we have the exam on 16th in June, June 16th. So please be prepared for the exam. So some problems like this may be given, or some different formats may be considered. Okay, made a, I didn't make the problems yet. Okay, so I'm thinking several styles. So the styles may be similar to those in the middle term, but anyway, the examples I'm showing were the problems in the past. So some new types of examples or problems may be given. Okay. Anyway, let's call it a day here and see you on Tuesday, June 9th. Okay. Thank you for listening and see you on Tuesday.